everyone. This is the summary session of the course Soil Mechanics Geotechnical Engineering 1. The last class of this session, the last live session, live discussion session by me was done yesterday from 5 to 7. And the topic was Introduction to the Stability of Slopes. And today I'm just doing a revision kind of session to cover up almost all the major topics in the form of questions and answers and a few important concepts, some numericals which are important. And this session has mainly conceptual questions from the previous sessions that have been covered in all the live sessions. And in short, it also has this MCQs, numericals, MSQ or true false kind of questions. It is a 1 hour question. I've already joined the meeting. It's already 4 o'clock, so I'll be starting the session now. This is the last session of the course Soil Mechanics Geotechnical Engineering 1. Alright. So yes, this is the summary session. I'll start the questions now. The first question of this session is, what is the type of soil formed after deposition in lake water? What is the type of soil formed after deposition in lake water? So in this question we have 4 options: alluvial soil, lacustrine soil, alluvial soil and marine soil. So we know that in the case of alluvial soil, the alluvial soil is formed after deposition from the river water. The sediments from the river water, when they deposit in the deltaic regions, then they form alluvial soil. Lacustrine soil is the correct answer over here because it is formed after deposition in the lake water. In the case of alluvial soil, it is formed by the action of gravity or gravitational forces. And in the case of marine soil, as the name suggests, it is formed by the action of seawater. So yes, the soil formed after deposition in lake water is termed as lacustrine soil. I hope the question was clear, the answer was clear. Go to the next question. Which of the following type of soil remain at their place of formation? It means when the soil is formed, that soil, particular soil, after formation, after the process of weathering in rocks, they do not need any agent for traveling because they stay in their place of formation and from the cover or the topsoil. This kind of soil which remain in their place of formation, they are called residual soil. They do not need any agent of transport. They do not need any agent of transport. In the case of aeolian soil, they need the agent of transport. It is wind. Wind is the agent of transport. Or soil transported by wind are called aeolian soil. Marine soil, I have already discussed in the previous question. It is transported by the action of seawater. And alluvial soil is transported by the action of gravity. So yes, this soil which remain at the place of formation is termed as residual soil. It's termed as residual soil. Okay. Next question. This is the first chapter. This is the origin of soil and their formation. This is the first chapter. And this chapter has all the basic concepts. This and the next chapter, 3-phase diagrams. Those chapters has the basic concepts of soil mechanics, which will be required in the subsequent chapters also. Okay, next question. The biggest size of clay particle is? The biggest size of a clay particle. The biggest size of clay particle is 2 micron. It is 2 micron. You can also say it as 0.002 millimeter. 0.002 millimeter. The biggest size of clay particles. Because beyond 0.002 millimeter or 2 microns, up till I guess 75 microns, we have silt. From 2 to 25 microns, we have silt, and below 2 micron, it is clay. So the biggest size of clay particle is 0.002 millimeter or 2 microns. Next question. Silty clay indicates silt percentage is less than that of clay. Silt and clay particles are in equal proportion. Silt percentage is more than that of clay, or none of these. So when we classify the soils and give them some nomenclature, the name of the first part is a kind of description to the soil. It is mainly composed of the second part. So here we can say when it is silty clay, it is a soil composed of mainly clay, and it has some particles of silt. If we say silty gravel, use a sign like this, GM. It is a sign like this. So silty clay will be like this. Silty clay, that is, clay particles are more in number and silt particles are less in number. Here also gravel particles are more in number, silt particles are less in number. So in this question, when we say silty clay, it means silt percentage is less than that of clay. Silt percentage is less than that of clay. It means that the soil is mainly clay soil. It is composed of clay particles, and it also has some fraction of silt within it. Hence, the soil is called as silty clay. I hope it was clear. I'll go to the next question. Among the given soils, the specific surface is the highest for. So before answering this question, we need to understand what is the meaning of specific surface. What is the meaning of specific surface? Specific surface, the definition of specific surface is surface area per unit mass. Surface area per unit mass. So, in a unit mass of all these samples, the one which will have greater surface area, that will have the highest value for specific surface. Now we know that on the basis of size, we can classify these components as gravel as the highest size, has more size than sand. Sand is larger than silt particles. Someone has joined. Yes, who have joined this meeting, I have already started the class. Okay, you it is just a revision class. Just copy down the answers. Okay, I'll repeat question number 2 to 5. Please mute yourself, Mohammed Tanveer Akhtar. Thank you. Yes, so this is silt, and silt is larger than clay. So clay has the minimum size, and hence a certain mass of clay, which is equal to silt and sand and gravel sample, the mass is equal to the gravel, silt and sand sample, that same mass, if the size is less, the number of particles will be more and it will have more surface area. It will have more surface area. And if it has more surface area to the same mass, then we can say that clay will have the highest value for the specific surface. So among the given soils, specific surface is the highest for clay, because clay will have the highest value of specific surface, because for the same mass of clay, silt, sand and gravel, clay will have the highest value for surface area, because it has the lowest size, it will have more number of particles in the sample of the same volume, of the same mass. I hope it is clear. I'll go to the next question. A soil has liquid limit of 20% and plastic limit of 14%. As per IS classification, what it means IS classification, the Indian Standard Classification System. The soil is, we have to classify the soil based on the value of liquid limit and plastic limit given. So the IS classification chart as per the plasticity is this one. This is the plasticity chart as per the Indian Standard Soil Classification System. We have plasticity index on the y-axis and liquid limit on the x-axis. If this is the case, then there is a line drawn from the point 20. It has an equation of the A line called the A line. IP, that is the plasticity index, equal to 0.73 WL minus 20. The straight line. Above the straight line, the soil are inorganic, and below the straight line, the soil is organic. Now there are two more vertical lines at liquid limit 35 and liquid limit 50. This vertical line segregates the soils of low plasticity, that is liquid limit below 35, intermediate or medium plasticity, that is liquid limit between 35 and 50, and soils of high plasticity, that is liquid limit more than 50, the soil will have low plasticity. Also, in this case, the soil below the A line might have silt in them, but it will never have clay. The soil above the A line is clayey soil, and the soil below the A line is silty soil and organic soil. But there is a small zone over here. This zone extends from plasticity index 4 to 7, and it starts from liquid limit 10 and extends till the A line. Now, as per the question given over here, what we need to do is we need to find out the point exactly where the soil sample is lying. So we have been given the liquid limit as 20. So if the liquid limit is 20 and the plastic limit is 14 in percentage, we can find out the plasticity index or IP by subtracting the plastic limit from the liquid limit. So liquid limit minus plastic limit gives us the plasticity index, and 20 minus 14 gives us 6. So it is 6%. So as per this graph, what do we need? We need liquid limit and we need plasticity index. So we have liquid limit of 20 and the plasticity index of 6%. 20 is also in percentage, 14% is the 6%. So we can now plot 20 and 6. 20 is the liquid limit, is this line, and 6 is this one. It is lying in this shaded region. And what we have in the shaded region, we have CLML, soils of low plasticity or low compressibility, and this is essentially inorganic soil composed of C and M. C means clay and M means silt. So in this region, it is the region from 4 to 7, this is 4 and this is 7, it is lying at this point. C and M, it can be clay, it can be silt, it has to be an inorganic soil, and it has to have low plasticity. It has to have low plasticity. So we can see that I have given an option. The options are inorganic silts with high plasticity, organic clays of medium to high plasticity, inorganic clays and silts of low plasticity, and inorganic clays of medium plasticity. We have only one option with low plasticity, which is also matching with the other criteria, that is inorganic soil and clay and silt. So this option number 3 is the correct answer. Option number 3 is the correct answer. So in this way, we can classify soil based on their liquid limit and plastic limit, or based on their Atterberg limits, which is being determined in the laboratory. So soil having liquid limit of 20% and plastic limit of 14% is inorganic clay and silt of low plasticity. Inorganic clay and silt of low plasticity. Okay, I hope I was clear. Okay. So this chart is very important to understand, because based on this chart only we can classify the soil with their liquid limit and plasticity index. And the equation of the A line is also important. I have given one question with respect to this A line also. Yes, this is the question. A soil has a liquid limit of 30%. The corresponding plasticity index given by the A line is. So to find the corresponding plasticity index given by the A line, we have, this is the equation of the A line, IP equal to 0.73 WL minus 20. So I will write the equation of the A line here. The A line, it has this equation, IP equals to 0, yes, IP equal to 0.73, yes, IP equal to 0.73 WL WL minus 20. What is WL? WL is the liquid limit, and in this sum, the liquid limit which I have given, the value is 30%. 30%. So it will be how much? 0. It will be 0.73 into 30 minus 20, 10. The value will be how much? 7.3. Value will be 7.3. So a soil having a liquid limit of 30%, the corresponding plasticity index given by the A line will be 7.3. That is the third option. 7.3. So this equation of the plasticity index is very important to remember when we need to find out, when we need to classify the soil based on this particular chart, plasticity chart by Indian Standard Soil Classification System. This chart is very important, and so is the equation of the A line. I hope I was clear. I'll go to the next question. Yes. The maximum water content at which a reduction in reduction in water content will not cause a decrease in the volume of soil mass. This question is easy, but we need to understand the concepts of this graph to answer this particular question. Because only the right option is not correct, we need to know the other options and what do they mean also. So the concept behind liquid limit is, so when particular soil is having a volume, this is the volume BD, this is the volume of the soil BD, then if we start adding water, the volume remains constant in a particular state. After that, the volumes are increasing. The end, that is the liquid limit, is a state beyond which the soil will behave as a liquid. It will have negligible shearing resistance. It will behave as a liquid. As we start decreasing the water gradually, the volume also starts decreasing. This is the volume. Volume also starts decreasing. When it goes below the liquid limit, it comes in a plastic state. That means it is highly deformable. It is highly deformable. So below the liquid limit, the soil is in plastic state up till the amount of water called the plastic limit. Because below plastic limit, the soil is no longer highly deformable. It has attained a stiff state or a stiff condition. It is also called semi-solid state. Also called semi-solid state, stiff condition. Now, if we further decrease the amount of water below this semi-solid state, we come to the solid state. But before that, a point B is reached when, even after we decrease the water, the volume will not decrease, the volume will remain constant. This particular point is called the shrinkage limit, the point at which a reduction in the water content will not cause a decrease in the volume of soil mass. A decrease in the volume of soil mass. So, the maximum water content at which a reduction in water content will not cause a decrease in the volume of soil mass. The answer is shrinkage limit. The answer is shrinkage limit. I have already explained liquid limit and plastic limit. Plasticity index is nothing but the difference between liquid limit and plastic limit. So this graph is also very important to understand the relationships between the Atterberg limits and the corresponding states. Beyond liquid limit is a liquid state. Between plastic limit and liquid limit is a plastic state. The soil is highly deformable. Between shrinkage limit and plastic limit, the soil is still showing a decrement in volume with a decrement in moisture content, but it is in a semi-solid state. It has moisture to a certain extent, but is not deformable as in the case of plastic state. And below the shrinkage limit, there is no change in volume upon the reduction in moisture content, and the soil is in solid state. It is not deformable anymore because the volume is constant. I hope it is clear. I'll go to the next question. Yes, anyone is there? Mohammad Tanveer Akhtar. Are you there?
Yes, sir.
Yes, can you solve this sum?
Yes.
Hello? We have to find out the dry unit weight.
I will guess.
I cannot hear you. Hello? A soil mass compacted at a moisture content of 12% has a bulk unit weight of 18.73 kilonewton per meter cube. its dry unit weight in kilonewton per meter cube is, can you solve it?
Yes, sir.
Please solve it and tell me what is the answer. What is the dry
Okay, sir.
unit weight?
Okay, sir.
Yes.
16.72.
16.72. Wait. Yes, the answer is how much? The answer is the fourth one,
16.72.
right? 16.72. Yes, very good.
Yes.
Yes. So how did you solve it?
Gamma D equal to gamma D upon 1 plus W.
Yes. Dry unit weight equals to total or bulk unit weight divided by 1 plus moisture content. So in this case, what shall we do? We will write this formula like gamma D equals to gamma T or total or bulk unit weight by 1 plus W. Gamma T is 18.73 and W is how much? 0.12 is 12%. So 18.73 divided by, so it will be nothing but 18.73 divided by 1.12, get a value of approximately 16.72. This is the correct answer. I'll just check once. 18.73 divided by 1.12. Yes, 16.723. Approximately 16.723 in 3 decimal places. And the unit is kilonewton per meter cube. Okay, it is kilonewton per meter cube. So yes, the fourth one is correct. The formula is dry unit weight equals to bulk unit weight divided by 1 plus moisture content in fraction. Okay, all right. Next question. We'll go to the next question. In a wet soil mass, air occupies 1/6 of its volume and water occupies 1/3 of its volume. The void ratio of the soil is, air has 1/6 of the volume and water has 1/3 of the volume. What is the void ratio of the soil? Can you solve it? Tanvir,
Yes, sir.
yes, please solve it and tell me what is
Yes,
the
sir.
answer.
Fine.
Yes, solve it.
Option D.
Hello? Yes.
Yes, option D. One.
Option D.
D. D.
Option
One.
B. 1. Yes. The answer is correct. How do you solve it? Tanvir?
Volume of water and volume of solid.
Volume of void by volume of soil solids, right?
Solid.
Very good. Volume of void by volume of soil solids. Yes. So, in this question, we have been given the, just a minute. Yes, it's visible. The volume occupied by air. So, if we write like this at first, volume occupied by air, that is equals to 1 by 6. Suppose the volume entire, that the total volume is 1. So volume occupied by air is 1 by 6. Volume occupied by the water will be how much? It is 1 by 3. Okay. So volume of void will be equals to volume of air plus volume of the water. It is equals to 1 by 6 plus 1 by 3. That will give us a value of how much?
1 by 2.
Yes. Value of 1 by 2 will be 1 by 2. Now if volume of void is 1 by 2, volume of solid will be how much? Volume of solid will be total volume minus volume of void, that is 1 minus half will be half. So volume of void is half and volume of soil solids is half. Void ratio E equals to, we know, volume of void divided by volume of soil solids. That will be equals to half by half or 1. What would have been the answer of porosity? Then we,
1 by 2. Half.
yes,
1 by 2. Half.
1 by 2 or 0.5 or 50%, isn't it? Because porosity is volume of void by total volume, that is 1 by 2 by 1, that is 1 by 2, 0.5 or half. It is clear, right? Porosity void ratio equals to volume of void by volume of the soil solids. Volume of void divided by volume of the soil solid. Okay. Yes. So the answer here is 1. Okay. Next question. A particle size distribution curve with a flat portion represents. A particle size distribution curve with a flat portion represents. Can you tell the answer?
Gap graded soil.
Yes, gap graded soil. I have shown it in here. This is the gap graded soil, right? Because in this particle diameter size, from this particle to almost this particle, there is almost no percentage finer. There is almost no percentage finer. So if it is a horizontal line like this, then with this range, there is no percentage finer increment. That is, this particular range, over here is absent. So it is a gap in the soil gradation. It is called gap graded soil. What is the meaning of poorly graded soil? Tanvir?
Same size of particles.
And what is uniformly graded soil? Yes. Uniformly graded soil and poorly graded soil. What is the difference between uniformly graded soil and poorly graded soil? Uniformly graded soil is nothing but poorly graded soil. If the soil is uniformly graded, that means it has particles of similar size throughout. That is nothing but poorly graded soil. It is a well graded soil which shows that it has particles of almost equal proportions of all sizes. That is this one. covers a wide range, but in pole-layered infrared it covers a narrow range, almost like a straight line. Okay, but this is a curved line. It has inclination. That means it covers particles of a wide range. It is a well-graded soil, isn't it? Is it clear?
Yes. Yes.
Yeah. So well-graded soil is required because it has to have a, a, a good interlocking property within the soil particles so as to ensure good compaction and good resistance against the external forces. Okay, so we generally prefer well-graded soil because the particles of all sizes, almost of all sizes, so it gives a better interlocking property, which is essential during compaction and other strength parameters, increment of the strength parameters in resistance to the external forces. Okay, so this is a yes. The flat portion represents a gravitated soil. Yes, correct. Okay, next question. Soil at the toe of a dam has void ratio 0.62 G. There is a specificity of soil solids as 2.62. Assuming factor of safety 5, the permissible exit gradient is. Can you solve this? Try to solve this. Tanveer?
Sorry.
Yeah. Yes.
Sorry.
What is the answer?
Sorry.
Which option? I can't hear you properly. Your mic is. You please write in the chat box if you are unable to speak properly because I also cannot hear you. Okay. So I think there is something wrong. He has left the meeting. I'll just carry on with the session. Okay. So how do you solve this sum? We know that the formula for the critical exit gradient IC is equals to G minus 1 divided by 1 plus E. G minus 1 by 1 plus E give us 2.62 minus 1 divided by 1 plus 0 1 plus 0.62 give us 2.62 minus 1 1.62 1.62 1. So we have a critical exit gradient of 1. Now if we talk about the factor of safety, the factor of safety is equals to the critical exit gradient divided by the permissible exit gradient. Because if the permissible exit gradient is less, we'll have a more factor of safety. So in this case we don't have the permissible exit gradient. So that will be equal to the critical exit gradient divided by the factor of safety. The critical exit gradient is 1 divided by, it will be 5, and 1 divided by 5 is 0.2. So the critical exit gradient being 1, for a factor of safety of 5, the permissible exit gradient should be 0.2. Should be 0.2. I hope the solution was clear. So I'll go to the next question. And yes, this formula is very important. This is the main formula. IC equals to critical exit gradient equals to G minus 1 by 1 plus E. Okay. Next question. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in remolded state. The sensitivity of the soil is, so we know that sensitivity is unconfined compression test natural by compressive strength remolded. Now in the unconfined compression test we get the shear strength is tau in the form of cohesion, because we consider the friction to be 0. We consider the friction to be 0. This is the undrained shear strength. That is equals to this QU, that is the unconfined compression test strength, is the unconfined compressive strength divided by 2. So undrained shear strength equals to the unconfined compressive strength divided by 2. So we have the shear strength given over here. If we divide it by 2 in the numerator and denominator both, we get, or QU equals to 2 into CU, we can write, so we get a modified formula of CU natural by CU remolded. And what is CU? CU is the undrained shear strength, or the shear strength given over here. So it will be how much? It will be 45 divided by 15. It will give us a value of 3. So unsensitive clay has a shear strength of 45 kN per meter square in natural state and 15 kN per meter square in remolded state. In that case, the sensitivity will be the shear strength in natural state divided by the shear strength in the remolded state. This is 45 by 15. The answer will be 3. The answer of this question will be 3. Okay. I hope the question was clear. The solution was clear. I'll go to the next question. Okay, this is a combined question from compaction and consolidation. It is a theoretical question. It provides a basic conceptual knowledge about the differences between compaction and consolidation. The compaction is the compression of the soil by the expulsion of air from the voids in the soil. But consolidation is the compression of soil by expulsion of water from the void in the soil. So basically this is the basic difference. Compaction, it expels out the air from the void in the soil, and consolidation, it expels out the water from the voids in the soil. This is the first and the basic difference between compaction and consolidation. Compaction is a quick process. It is a quick process, and consolidation is a slow process. In compaction, short-term loading is required because it is a quick process. Short-term loading is required to expel out the air from the void in the soil. But in the case of consolidation, long-term loading is required. Why? Because it is a slow process and it takes time to expel out the water from the voids. In compaction, loading is dynamic because yes, it is short-term loading, it can be dynamic, it is not fixed because it is a quick process, and because consolidation is a slow process, what happens is static constant load is present for a long period of time, due to which the water gets expelled out from the void in the soil. Now, compaction is done purposely in order to get maximum dry density of soil, and consolidation happens naturally. So to improve the strength of the soil for foundation, for the creation of foundation, compaction is done in order to obtain the maximum dry density at the optimum moisture content of the soil. But in the case of consolidation, when a structure is built, then it naturally occurs due to the overburden loads from the foundations. And in continuation of this point, the last point is it is done before the construction of a structure to maximize the strength or the dry density of the soil. But in the case of consolidation, it begins naturally along with the construction work, as and when the structures get completed, their load act as overburden load on the soil, and because of that load, because of that pressure, the water gets expelled out slowly and gradually from the voids in the soil. The last 2 points, it validates the first 4 points, that is a slow process. Here long-term loading is required in consolidation, and the loading has to be static and constant. But in the case of compaction, it is the otherwise, because it is done purposely before the construction. So it is a dynamic process, and the loading is dynamic, and it is a very fast process. I hope it was clear. The differences between compaction and consolidation, major differences is clear. I'll go to the next question. This is a question from the earth pressure theory chapter. If a uniform surcharge of 120 kilonewton per meter square is placed on the backfill with friction angle of 30 degree, the increase in active pressure in kilonewton per meter square is. So here we have been given a surcharge. We have been given a surcharge of 120 kilonewton. 120 kilonewton per meter square is placed on the backfill with friction angle of 30 degree. The increase in active pressure is in kilonewton per meter square is. So at the first we need to find out the coefficient of active earth pressure. Just a moment. If anyone has joined the meeting, sorry for the interruption. There was a problem with the internet connectivity. Okay. So you can see here that Ka, the formula for Ka, that is the coefficient of active earth pressure, is 1 minus sine phi divided by 1 plus sine phi. 1 minus sine phi by 1 plus sine phi. What is the value of phi? Phi equals to 30 degree. Phi equals to 30 degree. So 1 1 minus sin 30 by 1 plus sin 30. 1 minus half is sin 30. 1 by 2 divided by 3 by 2, it is 1 by 3. It is 1 by 3. Now, if sigma surcharge is 120 kilonewton per meter square, then the increase in active pressure, that is P horizontal, will be how much? Will be Ka into sigma, or will be how much? 1/3, 1 by 3 into 120 will give us 40. So 40 kilonewton per meter square is the answer. 40 kilonewton per meter square is the answer. So again, I'll just repeat. We first find out the value of the coefficient of active earth pressure, that is 1 minus sin pi by 1 plus sin pi. It gives us a value of 1 by 3. Next, what do? We know the surcharge is 120. So the horizontal pressure or the active earth pressure will be equal to the coefficient of active earth pressure multiplied by the uniform surcharge, which is Ka into sigma. 1 by 3 into 120 will give us, it is giving us 40. So the increase in active pressure because of the surcharge is 40 kilonewton per meter square. 40 kilonewton per meter square. I hope it was clear. I'll go to the last question. In stability analysis, the term mobilized shear strength is referred to as. In stability analysis, the term mobilized shear strength is referred to as. The options are shear strength, maximum shear stress, applied shear stress, or none of the above. Now, mobilized shear strength means that part of the shear strength of the soil mass that has been utilized, that has been used up by resisting, when it is resisting the external shear force or the shear stress. So, the externally applied shear stress, that is tau, and if the shear strength is tau f, so I'll write like this. The shear strength, I'll represent the shear strength as tau f, and I'll represent the shear stress is applied as tau. Then tau f minus tau will be something that is left, residual, and within this tau f, tau is being used up to resist this particular shear stress. So this tau is termed as mobilized. Tau is termed as mobilized shear strength, and hence we can conclude that the mobilized shear strength refers to nothing but the applied shear stress or that part of the shear strength which is being used up to resist the applied shear stress, and it is equal to the applied shear stress. So the answer is option number 3, applied shear stress. Mobilized shear strength is equal to the applied shear stress. Okay. I hope the questions were clear, the solutions were clear. So thank you everyone. I am ending this session right now, and this is the last session of the course soil mechanics.